Latitude, 30 degrees, 20 minutes north. Longitude, 67 degrees, 10 minutes west. The place, a spot in the Atlantic Ocean, not far from the island of Bermuda. The temporary base of the Glomar Challenger, an unusual floating laboratory especially constructed to probe the fourth dimension, time. Our journey is through the moon pool on an oceanographic expedition of great magnitude. It was born of questions. How did the great division between land and water take place? Were the continents always here and the oceans there? Or was the surface of the Earth once quite different and changing even now? The answers are tightly locked in the sediments of the ocean floor. This is the laboratory. Every usable square inch of the Glomar Challenger, the first in a new class of drilling ships. Her crew, roughnecks, geologists, mariners, paleontologists, oceanographers, a conglomerate of specialists. Their mission, the coring of deep ocean sediment in water depths exceeding 20,000 feet. Their track charts cover the oceans of the world. First came the Atlantic, then the Pacific, and after that the Mediterranean and Indian Oceans. The expedition is broken up into cruises, each voyage lasting approximately 2 months. Each drilling site has been picked with great care, and the navigator pinpoints his position with the aid of a computer. It's part of a satellite navigation system, using radio signals received every 2 minutes from a satellite in polar orbit. Up to 15 fixes a day are taken, and each time, the navigator can locate his exact position within 300 feet.
Bridge Science Office, I have satellite navigation fixed for you. Time 0948 Zulu.
The major technical problem is to hold the ship steady over the hole for many hours at a time. Were it to drift off, once the drill string is down, the pipe could be snapped in an instant. The water is too deep for conventional anchoring and mooring, so another method must be used. The system is called dynamic positioning, and these sonar beacons, now being readied for the bottom, are a key part of it. They are battery-powered sound transmitters, and the high-pitched wobble they produce can be heard for miles through the water. At each new site, before the drilling operation begins, the beacons are weighted down and lowered to the ocean floor. The spot on the bottom where they come to rest will serve as a reference point for the positioning system. On board the Challenger is the brain of the system, a digital computer. Its input comes from 3 hydrophones that have been precisely placed beneath the ship's hull. The signals from the beacons reach each of the hydrophones at a slightly different time, and from this difference, the computer determines the ship's relative position. The moment it begins to drift from this position, the computer activates a combination of the ship's propellers and 4 side thrusters to move it back over the hole. The surface of the Earth has been changing from the beginning, and many believe that it once looked far different. Their theory speaks of 1 or 2 supercontinents, giant land masses that broke into fragments and then slowly drifted apart. It was the shape of the continents that first suggested it, especially the eastern coastline of South America and the western coastline of Africa. They appear to fit together. When a computer was used to analyze the shape of the continental shelves, the results were even more impressive. They revealed a 95% fit between these 2 continents. And on the continent of Antarctica, geologists have recently made a startling find.
Well, the first day that we were out in the field here, I went out to the outcrop over Colsack Bluff in that direction, and then went on to investigate some of the sandstone cliffs which crop out about a mile away. And while looking over these just to check out the geology for the mapping program we have, I found these small black objects which I thought were probably bones, but since I had only seen 1 bone before in my life, 1 fossil bone, I wasn't absolutely sure what I had found until I came back and showed them to Dr. Colbert.
And showed them to me, and then we all went out, well, what, about an hour or 2 later,
Yes.
and went over, and then we started finding bones all over the place. Well, these are bones of various amphibians and reptiles which lived about, say, 200 million years ago, more or less, and they are of the same type that are found in South Africa and India and South America, and that is why these are particularly important.
And the importance of these bones, of course, is in suggesting that there must have been continuous land connections between these southern continents.
A continuous connection between these southern continents. If indeed a supercontinent did break up, why did it happen? What could explain the spreading movement? What kind of an engine could drive such a giant mechanism?
One of the most exciting ideas of modern times is the bold concept that the floor of the ocean may actually be spreading away from the central ridges that go down the middles of the major ocean basins. A fine example of this is the Mid-Atlantic Ridge, which more or less traces the center line of the Atlantic Ocean. The idea is, in seafloor spreading, that new oceanic crust may be forming along the trends of these rises, much in the idea of a kettle of soup, pea soup, cooking on a stove, where the slightly thickened crust may represent the oceanic crust and the way it migrates away from an upward moving portion of the soup underneath.
Indirect evidence of seafloor spreading has come from ships towing magnetometers across the ridge and measuring variations in the Earth's magnetic field. The studies have revealed that moving outward on each side, there are bands of alternating polarity, frozen, as it were, into the rock during former times. These alternations may reflect the periodic changes that are thought to occur in the Earth's magnetic field, when the north magnetic pole changes to the south magnetic pole, and then reverses to north again. The pattern of the alternations on the seafloor is strikingly symmetrical on both sides of the center, and, like some giant tape-recorded message, may tell of the spreading out of the floor over the past millions of years. Proof of the spreading action might be possible if a series of sedimentary cores could be taken across the magnetic striping, and if the bottommost sediments could be dated as to age, and if the age of the samples increased as we moved out from the ridge, and finally if this age difference was the same on both sides of the ridge as we moved away.
Because of the soft sediments, we've decided to go in with a drag bit, and on top of this drag bit, we will have a stand of collars, 3 collars. At this point, we'll put in a bumper sub. As you know, this bumper sub has a 5-foot stroke, a 5-foot stroke, and at the top of this, at this point, we will have 2 stands. It's a little hard to draw at this point, but we will have 2 stands of 8 1/4 inch collars. These are 8 1/4, these are 8 1/4, and then we will put in another bumper sub. At this point, we will have 1 8 1/4 inch collar, and then starting on the top of this, to complete this stand, we will have a 7 1/4 inch collar, and then we'll take right off with our drill string to the top of the ship.
The tools have been made up, the ship locked on station, and now the long reach down begins. It is the most ambitious deep-sea drilling project in history, and behind these men on the rig floor are many participants. Supporting the project is the National Science Foundation, an agency of the federal government. Managing it, under contract, is Scripps Institution of Oceanography, and the subcontractor is Global Marine Incorporated. They own the ship and conduct the actual drilling operations. Scientific guidance for the project comes from a number of oceanographic institutions, from the members of the Joint Oceanographic Institutions for Deep Earth Sampling, and from many other universities which are cooperating in the project. For all concerned, part of the measure of success is drill pipe. Nearly 5 miles of it will soon stretch between the Glomar Challenger and the ocean bottom. after the other, the 90-foot stands of pipe are threaded together and lowered through the moon pool. 1,500 feet of pipe goes down every hour, and at every 12-hour period, an alternate drill crew takes over. Drilling is done by turning the entire drill string. In the same way it's done for oil. And coring can start as soon as the hollow bit penetrates the sediments. The drill string forms a hollow cylinder through which the cores are pulled up from the bottom on a wire line. The cores arrive encased in a plastic liner, and it is then that the real sense of excitement begins for the geologists on board. They say it's like being let loose for the first time in a library of civilization lost forever to time. The vital statistics go on immediately. The location of the site, the date, the depth. There will soon be thousands of feet to catalog and study. First, the cores are X-rayed to inspect properties that might be missed by the eye alone. Burrows of old organisms, now filled with minerals and casting a shadow. The natural radiation of the core can be measured within this lead shell. The amount of radiation present will indicate more about the mineral content of the sediment. How much potassium, how much calcium carbonate. To measure water content and density, the core is bombarded with gamma radiation. How fast do sound waves travel through the sample? Once this rate is known for each particular kind of sediment, it provides a key to understanding sound profiles of the ocean bottom. How compact and strong is the sediment? For this, the weighted needle of a penetrometer. Obvious characteristics like color come in for careful scrutiny. The shades and tints are compared with standard color charts and recorded in great detail. Since the color and many other properties of the core will change after it is stored, photographs are taken every 25 centimeters along its length. The scientific work here in the shipboard laboratory is only the beginning. From here, the cores will be transported to one of the two core repositories, that have been established on shore. Cores from the Atlantic are stored at Lamont Doherty Geological Observatory. Cores from the Pacific go to Scripps Institution. They are then made available to all interested researchers for continuing study. And now, the crucial work, the dating of the cores. This man is a paleontologist, and he's looking for things that are quite small and fragile. They must be carefully separated from the other materials in the sediments. To him, these sediments are an ancient burial ground. They enclose the remains of millions of minute organisms, bits of life that once floated on the surface of the ocean. That was millions of years ago. And when they died, their skeletons or shells fell to the ocean floor and became entombed in the sediments. Through time, the character of these simple forms of life has changed. And so, by identifying a particular stage in their evolution, the paleontologist can date the sediment in which they're found. As magnification increases, the particles of sand undergo an astonishing change, becoming the chambered shells of foraminifera and radiolaria. They come in a great number of species. They vary in size and shape, in the number of chambers, and their geometry. It is this variation that makes it possible to distinguish the thousands of different kinds that have lived and died during the past millions of years. Overlapping of types, the particular types involved, and the extent of the overlap, these are of great significance in determining the age of the sediment. And here is the story they told across the rise. In the South Atlantic, the age of the oldest sediments, just above the rock floor, grew progressively older as samples were taken further from the ridge. Fossil dating produces ages remarkably close to the estimated ages of the magnetic bands. And the rate at which new crust spreads was found to be from 1 to 4 centimeters a year, an average distance equivalent to your height during your lifespan. These findings strongly support the theory of seafloor spreading and rank as the first major discovery of the expedition. A second discovery has been made in the Gulf of Mexico. Cores drilled there in the Sigsbee Knolls contained oil, the first time it's been found in the deep oceans. All such drill holes now get filled with cement, so that no possibility exists for the oil or gas to escape into the ocean. And from cores taken all across the Atlantic, the history of that basin is coming into sharper focus. It now appears that this ocean is a relatively young feature on the planet. Its beginnings can be traced back no more than 200 million years. delve through the floor of the ocean. The practical consequences of such a fundamental study as this are easy enough to visualize. The oil and other seabed resources that are being located and identified may well be objects of ocean commerce in the future. The ocean designers have already built some of it to scale. For those involved with the Challenger, though, it is purely a matter of science. And from each day's findings come more comprehensive questions for tomorrow. Questions about the early history of the Pacific, about the interaction of continental and oceanic crust, and about the complex forces at work in the interior of the Earth. New answers are waiting at the bottom, and they are now within reach.